and Bob Gerzoff can talk about issues with the RBN Wsbr data analysis. So, hi everyone, welcome to the HamSCI Telecon. I've been busy putting in my personal space weather station, working on that this past weekend. I think I showed some people on Monday night what we were doing. Basically, my friend Jonathan Rizzo and I trenched about 250 feet of trench and put in some conduit in my yard that we're going to install at the other end, a ground magnetometer and a VLF receiver. So that is in progress. So we're working on that. So let's see, Steve Serwin.
Yeah, I actually have been not doing a lot of ham radio stuff other than some operating. I've been doing some work things. Antenna classes are going to be redone a little bit. One of the ones I do beginning of the year, end of this year, they're going to separate it into two groups, one double E's, one MEs. So I have to kind of flavor the classes a little bit for the two. And there's been a couple of projects, construction projects, work related, that I've been working on. And besides that, I've been tuning up my air rifles. I like to shoot precision air rifles and getting them to print like a dime-sized group at 25 yards, competition type stuff. But not just that, I hunt with them. These are big bore air rifles, and it's now legal in many states, including Texas. If your air rifle is bigger than 30 caliber, you can take deer with it. And I've taken about 4 with mine.
Wow, nice.
In fact, it's 4 for 4.
That's great. That sounds really good. Excellent. Bill Engelke, how about you?
Let me share my screen here. I will show you the latest thing that we've figured out here. All right. This is the planned architecture of the central control system, figuring how we try and accomplish making the system available and yet have the data with as much security as we can muster. So the user on the left, that's a local host, and it has occurred to me also, I probably need to come up with a version of the local host that will run a grape. But that's down the road a month or two. But okay, so the local host comes through a firewall to hit the PSW network UA server, which is in a DMZ area. So there would just open just the ports necessary to get to the web service and the rsync and SFTP ports. So you can, the local host will upload files of data as they are collected or in response to a heartbeat and a data request. So then as the data comes in, it will be checked on the web front end. Then the web front end will talk through a second firewall to the backend server, which is the HamSCI server. That's the one with 15 terabytes of storage on it. And the spectrum data will be stored in the bulk data area, and a database will be updated. We now have the basic fundamentals of that web server working so that you can sign in. While you request an account, it will send you an email. When you go, you get your email and then you verify it. That creates your account, so we know it's a valid email address. You can create a station and hang that off of a user. A user can have multiple stations, and hanging off of a station is 1 through X instruments. And those instruments are the data source right now. We have the 3 types of instrument the tangerine, the grape, and the magnetometer. We're going to, I suppose, add seismometers and meteorological equipment, and I don't know, God knows what all we could add. So anyway, so for this first go round, phase one, we're going to only support uploading data of specific frequencies, not arbitrary frequencies. It has to be one of the WWV stations, and you have your choice of running exactly on frequency or running down a kilohertz, which you need to do if you're running with a receiver that has running an upper sideband. So the WWV frequencies and the CHU frequencies, those will be the only frequencies that we support. If somebody sets their system to collect data of other types for phase one, that upload would just be dropped, because we want to start out with I don't know, you got to do some data checking, and until we have more sophisticated ways of verifying that of the reality of what people are uploading. Besides, I think with the science we're trying to do, this is sufficient according to my understanding for phase one. Now, there may come a day, and we are already starting to talk about how to tie Amazon Web Services into this. If we come a day when we start trying to upload big chunks of spectrum, like many megahertz at a time, we're not going to be able to do that using UA servers because the capacity isn't there. So we'll have to, this would be assuming that what I'm talking about now would be assuming that the NSF is happy enough with what we do in phase one to fund a significant follow-on project, which would be large enough to provide funding for cloud services. And that would be good because it would take some of the load and stress off of our local server farm, which really isn't designed to necessarily be a big commercial cloud. It's more university researchy kind of thing. So anyway, so that's what the latest couple of things. So back to Ned.
Thank you very much, Bill. That sounds great. Let's go over to Michael, A8K.
Oh, thank you. Greetings to everyone listening. Back to you, Nathaniel.
Thanks, Michael. And Gary, AF8A.
Hey, good afternoon, everyone. And now that Bill has that beautiful plaque, this QSL card, I may have to list this on eBay or something and see what. That's from the January 2000 North American QSO party, by the way.
Cool. Very good.
Pretty old. Speaking of Y2K, I just found on the internet an unopened new old stock NorCal QRP rig surface mount version. I've never done surface mount before with the grape and all these other things coming out. This will give me an opportunity to increase or improve my tools downstairs to get that thing going. The other thing is I'm waiting for the postman to drop off my Tapper Raspberry Pi hat for a Wsbr transmitter. So one of these days I'll be generating data too. So lots of good things happening for when the weather turns south. I'll be able to keep busy indoors. So back to Ned.
Thank you very much. And David McGaw, N1HAC. Are you there, David?
Negative audio.
Anything? Hear me?
You're really quiet, David.
Okay, well, not
That's
much I
better.
can do with that. I'm coming through the phone. Yeah, welcome to the Barrel Lab. Trying to get a temperature change working here to take something down to -60. I've been using it for years, and all of a sudden it's decided not to work. But oh well. I'm working on what ultimately should be the power system to power one of the grapes. Kim wants to send one of those down to Antarctica, eventually to the Korean EGO. And I'm working on the power system for that.
currently a rebuild and then a redesign. Then Bob Melville and I are about to go over to the Nearfest amateur radio flea market for the first time in 2 years. And hopefully we'll stay safe. Should be outdoors, should be safe outdoors. So we're gonna have fun this weekend. Back to net.
That sounds really exciting. Please tell Bob I said hello.
Will do.
Thank you. And JB?
Yes, hello everyone. Good to see you. Since we last spoke, I had a number of interesting exchanges with Gwen Griffiths. And basically, we discussed what kind of open questions, after having read his material, we discussed what kind of open questions he might want to address next. I queried him about that. And within context of our discussion, it kind of came out that my greatest interest was actually in the noise itself, in the character of the noise that's being measured in this project. And I think we both agree that there's a number of there's a mix of processes potentially involved here. And it occurs to me as a newbie to this entire thing, but a scientist nonetheless, that if we're to draw any conclusions from these measurements at all, we have to know what this noise is. And there's a number of possibilities, of course. There's solar, there's cosmic, there is planetary, like Jovian, and then there's also the self noise of the ionospheric plasma itself. And so over the ensuing few days, I've been thinking about, well, how does one characterize this, and how would we pick this apart and figure out at any given time which noise process or which of these noise processes are predominating? And then, of course, the follow-on question is, what kind of, so we've done all these noise measurements, what conclusions do we draw from this in terms of the impact the ionosphere is having on radio communications? And I'm still thinking about this. So I haven't come up with any bright ideas as yet, or at least none that I'll admit to. But it occurs to me that if one indeed were to attempt to characterize these noise processes, which I think, given past work, I think we can be pretty sure that they're all present. But it occurs to me that we probably shouldn't be looking, or if you're going to characterize the noise, you shouldn't be looking at narrow spectra. We'd be looking broadband. And so the idea is to figure out how to do that, one. And then number two, there's the question as to whether or not we should be looking at signal-free intervals. If we have a coherent signal that we can, in a sense, count on, maybe we can indirectly, because we can calculate FFTs galore easily using GPUs, arrays of GPUs, what have you. Maybe that's the way to extract some information about the noise. Anyway, that's how I'm thinking, and anyone else that wants to pile in on this, I'd appreciate it. Back to Ned.
That sounds really good. Well, when the Tangerine part of the personal space weather station comes about, then that will be an opportunity for doing wideband noise measurements.
And so these are passive. You're not using any coherent source. You're not looking at coherent sources.
That one, well, it depends. If you're for the Great Personal Space Weather Station, we're looking at WWV, so we're looking at that coherent source, but that's very narrow band. Over a wide band, I don't think we'd be looking at a coherent source. We would,
or a number of them,
perhaps. Or
perhaps.
a number, yeah. Or that could be something that could be developed.
Yes, well, let me think about this a bit more. I promise I'll have something more interesting to say next time.
That sounds great. Thank you.
Thank you.
And then Bob, WK2Y.
Hello, everyone. I am just recently back from a brief sojourn to Greenville, South Carolina. I and the XYL decided we absolutely had to get away for a short bit. And turned out to be, well, first off, we hit the fall festival there, had about 7 stages with jazz, rock, and all kinds of music. So that was good timing. We hadn't intended, and it's a great town to go visit. Ham radio wise, I've been crunching numbers with Diego, or I just got some data from Diego and crunching numbers and coming up with some things I will briefly go over. And then I've also been torturing some data, WSPR data, and I have a brief informal presentation on what I'm doing. And you can all tell me if I'm barking up a wrong tree, or if there are any useful pieces of information you think that I should be aware of. Don't hesitate to say so. So Nathaniel, if you'll give me the, how do I, let me see, I'll share, do I have, all right, so I'll share screen. And it says I will share screen. Oops, let me get my slideshow up first. Okay. Now I can't see the, all right, let's try this again. Share screen. I will share screen 1. Share. And now I will try and come over here. Well, I don't want to give away the punchlines here if I can help it. Why can I not go into slideshow? Ah, all right. Is everybody seeing my screen?
Yes.
Okay. So I'm titling this, for lack of a better title, an exploration of short-term variability associated with sequential matched WSPR observations. And you'll notice that I have underlined the word exploration. I don't have a particular hypothesis in mind. I have an ecological problem in front of me, and I'm trying to see what I can glean from the data itself. Sort of a backwards approach to the typical scientific approach, but if we knew what we were doing, it wouldn't be research. So my motivation is, I think Nathaniel made the distinction between operational and theoretical, and mine is pretty much an operational motivation. I'm a ham radio operator, and I want to know why a signal that seems to be there 1 minute disappears the next. And can I understand the processes that are underlying that change in signal strength, signal clarity, etc. So, as was just mentioned, there's an infinite number, and I don't believe I'd be exaggerating when I use the word infinite, number of potential explanations and influences. There's solar, there's meteorological, there's station-to-station differences, antenna differences and temporal differences, geographic differences, and each one of those operates. There are differences within each one of those differences at different scales, both temporal and spatial. So that's why I say it's probably not unfair to say that there are an infinite number of potential reasons for changes in signal strength that I experience as a ham radio operator. That last line was supposed to be et al, but I guess I didn't quite catch that. All right, so my approach is the famous approach of all good analysts. We torture the data and ultimately it will confess. And I emphasize it will confess to anything. So if you have any preconceived notions, you will definitely verify those preconceived notions. I have my preconceived notions are perhaps even more dangerous than yours because I have no background information in solar physics, if you will, to lead me down the right path. Then again, that might be an advantage. I don't have any preconceived notions about what should or should not be driving it. Indeed, I don't even understand the data a lot of times. So if we're going to try and deal with this mass of potential explanatory variables, we want to control for as much as we possibly can. And so my thought was, and this is certainly subject to your criticism and revisions, but I want to control for as much as possible. So I don't want to look at Wsbr data measured, confounded with RBN data, confounded with HF data, who knows what, RTTY data. So I'm looking at the single mode WSPR. Later on, I can go back and look at another one. I'm looking at matched station pairs, same two stations on the same frequency over the smallest possible time interval. And for Wsbr data, that's about what, 2 minutes. I forget exactly what the cycle is. So I have built a database of pairs of stations on the same frequency, and the observations are between those two same stations, one right after another, 2 WSPR cycles. And then I'm looking at the signal to noise ratio of those. My outcome, again, as I just mentioned, I got ahead of myself a little bit there, is the difference in WSPR reported signal strength, signal to noise ratios between two sequential contacts between the same two stations. Now, to predict what is accounting for that difference, I have the kitchen sink. There are innumerable ones, and this is where I'm dependent upon Nathaniel and all of you folks to tell me what I should be looking at. There are some obvious ones, you know, day, date, the cluster of the stations, the two stations, their azimuth, those kind of things. But in reality, although I will find some things out, whether they make sense or not is going to have to be up to those who are more well-informed than I. The statistical approach that I'm going to be taking is a standard regression modeling approach. I have the joy, I'm a public health statistician in reality, and so I rarely get something like this. I have a continuous outcome, a signal to noise ratio. I have lots of data. One thing that needs to be taken into consideration is that these data are clustered by station pairs. And I see that ignored in many, many situations. The fact that I have multiple pairs and multiple observations for those pairs of stations says that I actually have less data than I would appear to have at first glance, because there's less information there because we have the same station pair that, and we need to reduce our testing parameters to account for those differences. We also need to account for the baseline. And then we have meaning, are we starting off at a low signal strength? Are we starting off at a high signal strength? And finally, the questions that may be really important is, are we interested in the entire distribution or the extremes? And you'll see why I raised that question. Obviously, two sequential observations, we would hope that the difference between would be very, very small between time 1 and time 2. And then as we go out in time, presumably the differences would get larger. But we're trying to get it down to the minimum here, and hopefully that would be a very, very small number. But you'll see that we have some rather large numbers, and it's a sizable proportion of the distribution. And the question is, why? And is that what we're really most interested in, or are we just interested in the entire distribution? So my data set includes all 20-meter WSPR observations between January 2017 and July 2021. I unfortunately retired and downloaded them all from Wsbr Live. I don't have a mega station, but fortunately a computing workstation, but I'm able to reduce the data set by finding all the pairs of stations that have observations within 2 minutes of one another. And that really resulted in 2,286,311 paired observations, and representing 85,287 unique pairs of stations. And just if anybody, this is sort of a one-off, LX1DQ and G0CCL, they had 33,098 observations between those two stations, and LX1DQ and OH8GKP. And one day I'll probably meet those guys and tell them that they hold some kind of record. I don't know what exactly to call that record, but let's see. So if we look at the distribution of signal to noise ratios from WSPR, you can see it's a rather skewed distribution. That tail goes way out there, way out to 40, but it's not too bad. And when we look at the difference, if we're taking the difference of two random variables, we come up with a even more random, a more normal variable. Two random, we wind up with a normal variable. And here we get the distribution, and you can see that the mean is pretty darn close to 0. But we have some reported observations as where the difference was -64 or maximum of 67. Now that's nice and symmetric, but a difference of that large, is that realistic? And the interquartile distance is -5 to 5. And even that is a rather large difference. So I have been plugging these into some modeling efforts here. There's some interesting things starting to fall out, but before I go any further, I'd be curious to see what you think about the utility of this exploration and the utility of this modeling. Oops.
If I may make an observation on that last slide.
Please.
That distribution looks Ricean. It looks like it's the same kind of distribution you get. Well, I think the fundamental model is difference of two exponentially distributed variables. That's interesting to me. You might be seeing some new physics here. I don't know.
Okay, honestly, I am not familiar with that distribution, but I will certainly take a look and see what if it's applicable. That may be it's not something I'm going to have to, doing my standard stat packages, but I'm certain I could find something in R that will allow me to model that.
Or generate it. I mean,
Yeah.
yes, that's really interesting. That's actually quite clean.
Yeah, well, if it was pure noise in the SNR and you take a difference of it, you wind up with something that's even cleaner. So that's just, basic stats. So yeah, but exponential distribution does make sense.
Difference of.
Yeah,
Right.
Yeah.
Interesting.
Have you looked at the distribution, say, compare a day distribution versus a night distribution or different seasons?
Well, my models that I've been building incorporate time of day. I have to do, and they incorporate month, year, day, to the extent that you can do those without overlapping in the variables. If you incorporate day, you're somewhat incorporating month, and if you incorporate month, you're somewhat incorporating year. So you have to be careful when you include all those in the model. But yeah, I am looking at that now. And the day actually, of course, you can see the effects, but let me just summarize everything that I found so far. All the things that are the obvious predictors account for an extremely small percentage of the overall distribution. I mean, less than half of 1%. They're significant because we have a huge database, huge number. But if you look at how much is actually being predicted, how much of that total distribution is actually being predicted, it's less than 1%. And I still have to sort it out and make sure I get things right. Time is actually, circular. You come back around to the same time, as is azimuth. And there's also a question of if I model something, should I be looking at differences in the absolute, or should I be looking at differences accounting for the fact that sometimes they're positive and sometimes they're negative? From an operational standpoint, I don't care if it goes up, it goes down, but perhaps there's some information contained in the direction of change, in addition to the fact that it's of a certain magnitude.
Yeah.
So there's a lot more work I need to do, and this is just, like I said, to get the thoughts out.
Yeah. But basically what you're doing is you're looking at short-term variability.
Absolutely, yes.
Stations.
Yep. Because everything else, there's so many other things. I mean, this is the only way I could think of to try and account for the fact that there's so much. I mean, by looking at those pairs of stations, I exclude variability, geographic variability, except for variability that I can account for, or I can then model it because I have the clusters of the stations. Time is no longer a big issue, except at the scale that I'm interested in, the 2 weeks. Space, time, day, date, it's all accounted for there. Those two sequential observations are happening on the same day, the same date, and the same season. So we get to account for those by looking at different pairs.
I guess I'm curious, by trying to split it up into day and night, or different hours of the day and different parts of the year, like, can we say that there's more variability that shows up at night than during the day? Because I know with like the grapes, where we've been looking at the TIDs, we generally see a lot more variability at night than during the day. So do you see the same thing here?
Yeah, well, those are questions that are easily answered. So I'll I'll run that and get back to you.
That sounds great.
And I think this is consistent with what Nathaniel said. Also look for dynamics or changes in the distribution parameters, mean and variance. And maybe that can tell us something as well. Under whatever circumstances.
Right,
Mm.
right.
Yeah. Yeah, because maybe if we can recognize some patterns, and maybe we can point to something.
Yes.
Mm-hmm. Yeah, I tend to get off into the modeling, but these simple questions maybe are undoubtedly a good way to get started.
Because then if it's just you see the same sort of variability all of the time, then is that there's just this constant variability in the ionosphere? We know things are sometimes more variable than others.
And what would that say? You know, let's suppose I looked at it and said, well, guess what? Doesn't matter day or night. With these particular measurements, I can have just as variable, two sequential observations just as variable as I could, you know, in the day or in the night or any day of the month or any season.
Yeah.
I'll wager that's not what you find.
I agree with that.
Now, what's interesting, I know, I'm just recalling some of the things that I was running here. I read there was a big difference in 2019, and I still don't know what that was from the other compared to the other 3 years. There was a shift in 2019, and you know, between 2017, 18, 19, 20, and 21. And 2019, for some reason, was more variable than the other years. And I want to verify that, but that's, you know, I don't know if there's anything that if anybody has any thoughts about what that was. Was there, and it made me think, was there a change in the software or a change in the SNR algorithm, reporting algorithm in that particular year that anybody knows of?
I don't know. But if there is, I mean, was after you saw that change in 2019, did that change continue in 2020 and 2021?
No, that's the odd thing. It was just 2019 was kind of, it was higher. The variability was a bit higher in that particular year. Maybe
Joe
that's
Taylor would know.
Yeah, I'll have to drop him a note. You know, maybe it was meteorological. I don't know.
Yeah, I'm not sure either.
We may wind up generating more questions than we answer, but any other questions, comments, thoughts? Is anybody still awake?
No, I'm trying to follow, and I'm probably 6 steps behind a little bit. When you talk about these station pairs, and
yes,
you control for the geographic differences. Some are at the same latitude, some are at different longitudes, and the sun's going to cross their positions at different times.
Right, and that's the reason for looking at station pairs. So the observation is here's 2 stations, and I get time 1, the measurement, and then a minute and a half later, I get another, I have a repeated measurement at that same pair of stations. So,
but when you show
yes,
that distribution, when you show the distribution plots, those distributions still had all of your different station pairs.
All of the different ones.
So
right.
I mean, there's still, you know, there still are going to be geographic differences. Like you could have places that have more ionospheric variability than others.
Right. But now that I'm looking at those pairs, I can incorporate something into the model and look at latitude. And I can look at and say, you know, is the variability varying by latitude? Is it varying by azimuth?
Yeah. I would guess that my hypothesis would be that station pairs that have midpoints closer to the equator and midpoints closer to the auroral zone are going to be more variable than ones that have midpoints in the mid-latitude region.
Closer to the equator and closer to mid-lat and closer to the
Auroral.
auroral zone. Okay.
The auroral zone I can understand. Why did you say the closer to the equator, Nathaniel?
You get a lot of in the equatorial region, you get a lot of these like equatorial plasma bubbles and instabilities that pop up more often
Okay.
than you do. There's something called equatorial spread F. So you get more of that closer to the equator. So equator is also considered a fairly active region.
Got it. Thank you.
And speaking of equator, I think that if you can identify pairs that are trans-equatorial, I think you're going to find something genuinely different in terms of your error bars. I think you're going to find something different because anecdotally we look for trans-equatorial propagation when we're working DX, and we can count on it, or we can expect it in certain seasons and what have you. So that would be really interesting, actually.
Okay. Nathaniel, I'll probably be bugging you to or some Diego to figure out. I know how to figure out Latin long in the azimuth. Well, azimuth is already there. How I figure out that it goes trans-equatorial, I may have to pick your brain.
Well, I guess the simplest way,
If it's plus and minus.
yeah, if it's plus and minus.
Yeah. Now that I've said it, I realized, yeah, duh.
But I mean, it does get more complicated than that, because usually when you're interested in the equatorial region from an ionospheric point of view, you're interested in where the magnetic equator is, and there is a dip that goes that the ionosphere follows. I could probably find a picture that illustrates this.
Uh-oh.
Yeah. Wait, oh, this is.
I just had it figured out. You're going to complicate my life?
Yeah, I'll complicate your life. I just did a Google image search for IRI Ionosphere, NASA Scientific Visualization Tools. So this is the International Reference Ionosphere Model. And you can see here's the United States, here's in North America, here's South America. You can see that the equator, the magnetic equator, is actually shaped in this dip here. So in South America, the magnetic equator moves, I guess, farther south. And then the colors that you're seeing here are ionospheric electron densities. So you actually have higher densities just north of the equator and just south of the equator too, because the ionospheric plasma will get pushed up by electrodynamic forces up away from the Earth, and then it will, when gravity takes over, the plasma will fall down these magnetic field lines into these higher density regions.
Okay.
Wow, and I think I just get on 40 meters and call CQ and hope for the best.
It works.
It works, yeah.
So there you can really see that shape, the magnetic, the equatorial dip shape.
Sorry, 40 meters is a mess these days.
Why is 40 a mess these days?
Well, on FT8, which I happen to work a lot of, there's just the QRM is just crazy. And then with the increased solar activity, the propagation can get really wacky.
See, that's why it doesn't pay to have a good antenna.
Yes.
If you can hear them, then.
I like what you're doing though, Bob. I haven't thought about doing it that way. So I think it'll be interesting to see if you can pull out any patterns that do show some sort of seasonal effect or solar cycle effect. You know, we now have enough Wsbr data that you can look at solar minimum versus solar maximum as well.
Okay.
See if there's more variability. So like one thing that I thought of is, I think
you can actually get more of these like high speed streams during solar minimum, or as you go into solar minimum, not right at solar minimum, but as you go the down part. So I was wondering if year 2019 had something to do with that, but I think it was too much in the minimum. I would be very surprised if that was the actual cause.
Yeah.
But you certainly could look at solar max versus solar min, you know, the summer versus winter, autumn versus spring, day versus night, and you can look for patterns in the variability.
Right. The message that I'm getting is, again, you know, I'm jumping ahead of myself all the time, but these simple questions here are apparently going to be very useful. So I'll focus on some, you know, simple models and present those and see where they suggest going.
I think that sounds great.
All right.
I think so. We're almost at 4 o'clock Eastern time. So any other questions for Bob?
If anything occurs to anyone, feel free to drop me a note.
Yeah.
WK2Y. It's Bob at bobgerzoff.com or WK2Y at ARRL.net. So.
Oh, and I guess we can look at some of your questions that you sent me.
Oh, right, on Diego's stuff.
Yeah. I think my view of these things is probably rather simplistic, but you say as SIMH increases, do you expect the probability of a TID to go up or down or be unaffected? And similarly with AE, I think as SIMH goes up or down, I don't expect much of an effect. And I think when AE increases, I expect to see some more TIDs.
AE increases, TIDs increase.
I think so. Because the idea is there's a lot of papers out there that say that the aurora, particle precipitation and joule heating and auroral activity is a source of TID energy.
Okay.
So like the aurora happens and you get more energy dumped into the auroral zone that launches these gravity waves, and that can generate these TIDs. And the AE is supposed to be a measure. The AE is a measure of the auroral electrojet currents. So when there's more auroral activity, the AE index goes up.
Right. And do the two interact at all? Those two measures?
There's some relation between the two. SIMH, I think generally, SIMH generally measures currents that are occurring farther out in space and more in the equatorial region. So if you have a big geomagnetic storm, SIMH will increase. When you do have a geomagnetic storm, you can sometimes have more auroral activity too. So then you would also expect to see more increases in AE.
So one leads to the other? Is this a causal pathway? SIMH causing AE, and then there's a portion of AE which is independent of SIMH?
Yeah, I think there's a portion of AE that's independent of SIMH.
Okay, and but there's also another portion which is
related.
linked. Okay.
How would the impact of AE and SIMH vary by band? I'm not really sure. When SIMH gets lower, that's when you're more into the main phase of a geomagnetic storm. So that's similar, and you expect KP to be going up. So then you expect very often the electron density would reduce. So you expect more ham radio operators to move to lower bands because that's where the propagation is probably going to be better.
Forgive me, I'm taking notes.
But I'm not sure how that impacts the TIDs.
All right, well, we'll play, and as I said in that early slide, torture the data and see if it confesses to anything. You're keeping me off the streets.
Somebody has to.
Yeah, well. That's all I got. It was that was all the questions for the time being, right?
I think so. Thank you very much, everybody.
All righty.
Say
Good
73
session.
for
See everybody in
today.
a few weeks.
See you.
Ah,
Thank you.
73.
73.
73.